From IMPA in Rio in 2001 under the supervision of Wellington Amello. He initiated his career in France, first as a postdoc at the prestigious Collège de France. Then he became a researcher at the French CNRS, first as a chargé de recherche and then as a directeur de recherche. He was actually promoted to directeur before he was 30, which is a very unusual event in the very cautious career system of the CNRS. Since 2009, Artur holds a joint appointment at the CNRS in France and at IMPA in Rio. He has been awarded several prizes and distinctions, of which I will mention only the Solem Prize in 2006, the European Mathematical Society Prize in 2008. He was a plenary speaker at the International Congress of Mathematicians in Hyderabad in 2010. Last year, he was awarded the Early Career Award of the International Institute for Mathematical Physics. And last week, he was the first recipient of the Brazilian Math Society Prize. Artur is a mathematician with the heart of a dynamicist and the mind of an analyst. What I mean by this is that the kind of problems that he has been working on and solving usually originate from dynamics, but in order to achieve a solution, he develops very powerful tools in analysis as well. The scope of his contributions to mathematics is striking. He has given major contributions to such fields as low-dimensional dynamics, where he wrote his thesis, to the spectral theory of Schrödinger operators, where he brought the local theory close to completion and essentially single-handedly initiated a global theory that addresses the whole parameter range. It has also given major contributions to the theory of interval exchanges. And as we heard this morning in Amy Wilkinson's lecture, he also has major results in smooth dynamics, particularly concerning partial hyperbolicity and the ergodicity problem. What is perhaps less obvious to the eye is that his work has a remarkable unity. In fact, most of what he has done deals around the deep concept of renormalization, which is a fundamental notion in physics, which has been exploited in great depth by many mathematicians, but I think it's fair to say that Artur's work on renormalization has raised this concept to a whole new level as a unifying principle between different aspects of mathematics. And quite consistently, today we'll speak on Poincare series and renormalization. Artur?
Okay, hope it's fine, all right? Okay, thanks Marcelo for the presentation. I'm going to, I chose a topic that I don't talk very often, which in low-dimensional dynamics. It's going to be all joint work with Misha Ljubich. There are two microphones. I hope that's on. It should be fine. All right, so let me introduce the subject. So there will be it should be around the quadratic family initially, and you have well, I'm going to explain this picture to introduce. I think that I shouldn't assume much familiarity with dynamics, and particularly with complex dynamics, and so this kind of representative picture of the complex quadratic family is a one-dimensional dynamical system. And so what you have is polynomials z goes to z squared plus c, which have a single non-degenerate critical point. So, so those are the base dynamical systems that you are interested in. And what you see immediately is that if for large values of z, you fix the polynomial, then the iterates. So if you take z large, then when you apply the polynomial, then initially you take the square, and then you adjust a little bit, and it gets even larger, the norm. And this means that as you iterate, you're going to approach infinity if you started sufficiently far. This is not very interesting, so what's interesting is the set of bounded orbits, so which called the Philadean-Julia set, which has the set of orbits that don't go to infinity. And what you should think, you see pictures immediately, it's always a full compact set, so it doesn't have holes and doesn't have isolated points. So there is basically two possibilities initially. Well, there's a lot of richness there, but the initial two possibilities that you have is whether the critical point 0 belongs to the Julia set, and in this case, the Julia set is connected, like this in this picture, or the critical point is not in the Julia set, and then it's totally disconnected. That's a Cantor set. So that's an example of a disconnected Julia set node. There are some kind of blocks, and we don't see very fine to see the Cantor set, but you see some approximation of it here. So there's this basic dichotomy, and the Mandelbrot set is like the map of this dichotomy. It is the set of parameters C such that the Julia set is connected. So it's the part in black and its boundary that's there. It's a closed set. And what you see in blue in the outside is just kind of some potentials that help to see the details of the Mandelbrot set. Everybody saw probably this picture. I'm just recalling what it means. So basically, if you investigate this Mandelbrot set in several parts, and you just kind of put in the in Google or something, you're going to see very nice parts of the Mandelbrot set. And one of the most interesting features that you see from time to time on those pictures are those little bugs that appear here. This is kind of near the real line, somewhere to the left. You're going to see this little bug that looks pretty much like the whole Mandelbrot set. It's going to be called eventually a little Mandelbrot set. If you look at the complex, this is kind of near downstairs somewhere. You find this kind of little Mandelbrot set as well. It looks pretty much like the original one, also with a little bit of distortion. But this is sane. And then you want to understand what is the cause that, why are you seeing this picture? So this was understood by Douady and Hubbard in the early 80s. And they saw that it was generated by a renormalization phenomenon. So of course, I spent 3 years ago, I spent a whole lecture just to explain a little bit of renormalization. Here I have to condense just in the beginning of this talk. What we have, basically, what is renormalization is in dynamics. It's something that you apply to systems that when you look at a small scale and for a very long time, it happens that what you see after rescaling time and space, you see a system which looks like the original system qualitatively. So this kind of class of renormalizable system that you can apply this renormalization operator and get the original class is a very specific class that appears from time to time in low-dimensional dynamical systems. And here's going to be an example. The fact that you're going to see, here's a picture in parameter space. It's kind of less pretty to see the same picture in phase space, but there is that you can see, let's say in phase space, little Julia sets that reflect the fact that there are some parts of the dynamics that behave like the dynamics of an entire quadratic polynomial. So that's what is going to be the explanation of this picture. But to understand what, to explain correctly, you have to have in mind that what's the notion of what's to be dynamics that's like the original one. It's not to be a quadratic polynomial, because once you start iterating quadratic polynomials, you don't have a quadratic polynomial anymore. You have a polynomial, but very high degree. So you have to take something that quadratic polynomials have that's kind of more qualitative, and this class will have. So the class that was introduced by Douady Hubbard is the quadratic-like maps that are characterized by a topological covering property. So they're holomorphic maps from one disk to a bigger disk, which is, it's a double cover. It's going to, since it's a double cover, you have a unique critical point. And so this appears, if you consider a quadratic map and a round disk of very large radius, then you apply the quadratic map, it gets an even bigger disk, much bigger radius, and then you adjust a little bit by changing the constant. But anyway, it should be a covering over still a very large disk, bigger than the original one. So this gives rise to a quadratic-like map. Of course, there are points, so there's a map from U to V, and there is points in the fundamental annulus, that's V minus U, that you cannot iterate anymore. It's not very serious. This corresponds to those points that are so far near infinity that now they are forced to go to infinity. So those are those points that you don't care about. What interests us is, again, the set of non-escaping points, the set of Z that can be iterated forever under F and never escape in the domain of iteration. So it should be a Julia set that will look pretty much like a quadratic map Julia set in a very precise sense. So there's a theorem behind this that says that quadratic-like maps don't just look like quadratic maps, but are kind of very intimately related, which is the straightening theorem of Douady-Hubbard, which says that if you take a quadratic-like map, and we're mostly interested in the ones with connected Julia set, it's going to be of the same class, it will be hybrid equivalent to a unique quadratic polynomial. It's called the straightman of F, which has with a parameter that's in the Mandelbrot set, so with a connected Julia set. So what's this hybrid equivalence? Is a notion of saying that this quadratic-like map is a deformation of the original of a polynomial. So you're deforming the complex structure to generate this quadratic-like map, but the deformation of the complex structure is outside of the Julia set. So you're not touching the conformal structure of the Julia set. So formally, you have a quasi-conformal map that conjugates the original quadratic-like map, and it's straightening the quadratic map, which is conformal on the Julia set. So that's the class of maps that you need to work on. And it's in this class of maps that you're going to be able to renormalize and get in the same class. So what happens from time to time among renormalizable quadratic-like maps is that there exists a little disk. So you have a disk goes to a bigger disk. But now you find a tiny disk near the origin that after you iterate many times, it comes back to a slightly bigger disk, or to a bigger disk, as a double cover map. So you can define a new quadratic-like map. And you're interested in the case where this new quadratic-like map has a connected Julia set as well. There is an additional technicality that I wrote, but it's not worth to read. But let's just point out that once you have this and avoid this technicality, you can define the renormalization of a quadratic-like map is if it's possible to find this disk, then in principle there could be several ways, several scales where this happens. You take the largest scale that corresponds to the minimal P, which you can iterate to produce this quadratic-like picture. And you take this as the renormalization of F, consider it up to scaling. So there's rescaling of space that needs to be considered to consider. So usually you consider up to affine compositions of the map, affine conjugacies. So this is a drawing that later on I will explain all the colors. But what I did here, I take a quadratic map, and I look near the critical point. And you see this domain that so there is some red and light blue that you forget about. And there's a region that's there's black, yellow, white, and deep blue. And if you look at this region, you have a disk. And basically, the black region and the yellow region, it's mapped as a double cover over the larger white, mostly white region. And what you see in yellow is the Julia set of the quadratic-like map. So this is this was taken a renormalizable quadratic map, and this is exhibiting the quadratic-like renormalization of this map. And this particular one is relevant in this talk. So, and now how does it explains the pictures that you saw about parameter space, that the set of renormalizable parameters is disconnected. But and the connected component is what you're seeing this. A connected component is going to be called a little Mandelbrot set, and it's going to be canonically homeomorphic to M, to the entire Mandelbrot set. In the primitive case, that's going to be the only one that I'll be discussing in depth here. So this homeomorphism that appears is just that you have the original quadratic-like map, and you look, or quadratic map, you look at its first renormalization as a quadratic-like map. By the straightening theorem, it will correspond to a unique parameter in the Mandelbrot set. And this map that takes to this parameter, that's the straightening of the renormalization, gives the homeomorphism between M and M prime. So this explains the appearance of the little Mandelbrot set. OK, you have this, and you have this interesting homeomorphism. And what happens is that this canonical homeomorphism is going to have, under those conditions that I'm not talking about, this canonical homeomorphism is going to have a unique fixed point, which would be a very interesting parameter. Is a class that once you normalize, you get in the same class, a hybrid class. And in this map that takes a little Mandelbrot set to the big Mandelbrot set, it's going to be a differentiable at this fixed point. And you have a derivative of norm bigger than 1. So there, you're going to see this. And this differentiability will mean that if you keep looking in smaller and smaller scales around this point, you can kind of take this preimage by the successive scalings, this homeomorphism. And you're going to see smaller and smaller little, so inside this little Mandelbrot set, there will be a little Mandelbrot set that should be the preimage of the original one by this homeomorphism, and so on and so forth. And those copies will be kind of asymptotically self-similar. Due to this differentiability, there is some additional regularity that can be mentioned, but they are going to look closer, more and more converging to a asymptotic shape. And this is explained, the fact that all this is true is something that comes from the fact that the renormalization operator, actually acting on this whole space of quadratic-like maps, it's going to have some good class. It's kind of complicated space, but it can be made sense that it's a holomorphic map. And this holomorphic map, you have a unique fixed point in this hybrid class, which will have the property that it is, it should be C star somewhere, but this fixed point is hyperbolic with a single eigenvalue that will be precisely this derivative, which will be outside the unit disk. So this will be the expanding eigenvalue. All other eigenvalues are inside or it will be a compact operator as well. All other eigenvalues are inside the unit disk, well inside. And this will correspond to having a stable manifold that's codimension 1 that will be exactly the hybrid class. So as you iterate maps in the hybrid class of this fixed point, they are going to kind of converge under renormalization towards the fixed point. So that's why the behavior at the quadratic polynomial will be the same as the behavior that you see near the fixed point that will be ruled by this unstable eigenvalue. And everything that I said here is chronologically, it goes in several advanced to extend to one class to another and so on. It's due to McMullen, that's basically this convergence to exponential convergence to the fixed point. Lubitsch, that's the creation of the unstable eigenvalue. And Jeremy Kahn, that got a big class of maps, which is proving a priori bounds, a certain control of the renormalization that allows it to apply to all guys that have primitive combinatorics, which I didn't explain. So, but then this is a theorem. And now you see that there will be this remarkable self-similarity. And I just point out for kind of explain that historically this comes even from something was motivated initially. So historically, this comes from the 70s. Originally, people were interested on this top picture, which shows the bifurcation diagram in the real quadratic family. So where it appears that sometimes you have an attracting cycle, and then as you change the parameters, appears a cycle of period 2 that is attracting. And then there's this first bifurcation there. And then as you continue, there will be an attracting cycle of period 4, and so on and so on. And if you in the complex dynamics, it corresponds exactly to this kind of intersection of the real line of those kind of, so you have here's the main cardioid, and there's something that's kind of a disk, and then there's a new disk, and so on. And basically, what you have here is that you have a homeomorphism from this to this whole Mandelbrot set. So there's a little Mandelbrot set here that's kind of satellite type, unfortunately. And, but fortunately, we know that there is a fixed point here. And the fact that you have the Poincare phenomenon of exponential convergence with a given rate towards this asymptote of the bifurcations here corresponds exactly to the self-similarity around this point. So this theorem that I just mentioned before implies in a specific case that unfortunately falls out of reach of the exact theorem that I stated, it implies exactly this same behavior here in the quadratic family, which was one of the first times that renormalization was introduced conjecturally to explain a phenomenon in one-dimensional dynamics. All right, so, okay, so this is something that probably you saw, and there are many ways to find more about that. what you're going to be interested here is that the dynamics at the fixed point. So this fixed point of renormalization plays an important role in kind of this universality picture, and there are this kind of very nice geometry in parameter space. If you look at there will be a similar interesting self-similarity in the Julia set of a fixed point. Actually, some features of the Julia set will play a role in the understanding of the dynamics of this renormalization operator. For instance, in McMullen, he proved the following fact about this Julia set of the fixed point, and it's a kind of a bigger class of maps. That if you start looking near the critical point and you start magnifying the Julia set, you're going to get more and more complicated pictures. The Julia set gets denser and denser. So what's saying that it is going to converge in the house of topology to the whole complex plane, the sequence of magnifications, at a given rate that's going to be exponential. And in fact, this discovery of his will play a role in his proof from the 94 or something, of exponential convergence of the renormalization operator. So some fact about the geometry near the critical point corresponds to this, to this fact about the dynamics of in parameter space. And of course, this property will of the critical point being a deep point, that's kind of is this property of these magnifications that converge exponentially. It will persist through the hybrid class because of quasi-conformal invariance. Now here's a picture. So I try to make some pictures, but it's a little bit difficult to see good picture of the Julia set. If I painted the Julia set black, you're going to get just some pictures that are increasingly more black because of this theorem. So, but let's put some colors, and you see that the bigger complexity on the way that the colors change faster and faster means that the Julia set is kind of everywhere in this picture, getting everywhere. So you see here, the regions where the color is constant are away from the Julia set, and then it gets very complicated colors. All right, so this is illustrating what McMullen discovered. Now, what we are going to be interested here is rather the kind of more basic and immediate question that you could ask. So if you're interested in the geometry of the Julia set, the basic question that you start asking is it a set of really fractal dimension less than 2, for instance? Or is it kind of so complex that it gets dimension equal to 2? Right? It is a set of empty interior, and, but it has this complicated structure. It could very well have full dimension because of its complexity. And perhaps if it has full dimension, maybe it can even have a Poisson-Lebesgue measure. So that's kind of the most natural questions that you can ask about a fractal set such as this. And if you look at this complexity picture due to this deep point theorem, and which originated, in fact, from the fact that as you get closer to the critical point, you have different independent, basically, scales competing to iterate your map. You can iterate using several different renormalizations of your map. You are lying within several renormalization domains, and you have several scales of dynamics playing at the same time as you lie deeper and deeper, and this is that generates all this richness. You get in each scale, you can use the correct renormalization dynamics to produce your Julia set, and you get these Julia sets in many scales. But is it going to also imply that house of dimensions equal to 2? It's a good question, but there is a kind of more definite intuition. I'm talking about how people think of this in the 90s, a more definite intuition about what should be the answer to those questions, which comes from what's called the Sullivan dictionary. So the Sullivan dictionary is basically a parallel that's made between some objects in iteration of rational maps, like Julia sets of quadratic polynomials and things like this, and objects in three-dimensional for hyperbolic tree manifolds and Kleinian groups. So basically, there is kind of a parallel development that inspired, that derives, of course, that Sullivan's very successful in using this to give simultaneous proofs, basically simultaneous proofs of theorems like which, like in dynamics, the no wandering domain theorem and things like this, by looking at a result in Kleinian groups and applying the proof. Well, trying to mimic. It's of course very complicated in the end, but you can conduct it in parallel to get results in both areas. And if you look at this kind of dictionary, there are moments where it's quite unclear what takes from one side to the other side, but some things are very clear. The Julia set corresponds to the limit set of a Kleinian group. And it turns out that the fixed points of renormalization particularly, they correspond to some, and this kind of renormalization that you're discussing here, will correspond to some specific types of tree manifolds that have some kind of, they are geometrically infinite, but have some n that fibers over the circle. Actually, if you look at where McMullen wrote the proof of exponential convergence, it's in a book that's called Renormalization and Tree Manifolds that Fiber over the Circle, which is where many things are done, where this parallel is displayed. And like one problem that's analyzed for the case of tree manifolds would be construction of hyperbolization of certain tree manifolds. And this is related very much to certain things about the renormalization of fixed points and things like this. So anyway, so you have this dictionary, and what happens in the case of the Kleinian groups? There was the objects in the Kleinian group setting are often a little bit simpler and more amenable to analysis. Any Kleinian group setting, you see that the corresponding limit sets, they have a house of dimension 2 always, and Lebesgue measure 0. This was known even in the 90s. You don't need to use the proof of the Alfors conjecture, which is much more general. For the specific types of tree manifolds, it's kind of relatively simple proof, simpler proof. I think the consequence of Bishop-Jones may be a little bit earlier, but there was this that is always dimension 2, so the geometrical infiniteness implies the produce this kind of larger complexity that gives house of dimension 2, but on the other hand, you don't have positive Lebesgue measure. So it should be a fractal kind of just in this kind of borderline to positive measure. So that's what was an intuition. And people in the 90s, there was some kind of attempt to kind of push this analogy further. You see that the problem of rational maps that if you're working on Kleinian groups, you have the tree manifold to help you, the hyperbolic tree manifold. And you can conduct analysis using the tree manifold. There are things like doing Brownian motion in the tree manifold and things like this. And, but here for rational maps, you don't have the tree manifold. You just have the rational map that you can iterate. So what you could try to do is try to construct some object that would be three-dimensional in nature that would allow you to do things like run Brownian motion and things like this. And this object is kind of understood to be some three-dimensional laminations. So there are kind of 3D space that kind of times some kind of contour sets, and it should be something complicated like that, which unfortunately are very difficult to tame analytically. So never go to the stage that you could kind of produce a proof in this context. Anyway, so let's take a look at a slightly different direction that's going to be more grounded about this. How else could you approach the problem of looking at this? How could you approach more directly the problem of estimating the dimension of such a set? So then you get to the part of Poincaré series, was something that's introduced in a different context by Poincaré, and with different purpose, which has the base object. So this was from the original paper where he starts talking about this. He was calling fonction theta Fuchsienne, and he introduced the Poincaré series downstairs. But just to mention, so the object that you're considering is a Fuchsian group. So you have the hyperbolic disk, and you have a discrete group of motions in this Fuchsian group. So you have a discrete subgroup of the set of isometers of the Fuchsian group. And this is a class picture that appears with two generators and leading to a simple surface. And what is the original Poincaré series associated to the Fuchsian group is an expression like this. So you start with some holomorphic function here, and from this holomorphic function you want to get some object that has that transforms nicely under the Fuchsian group. So to get this, you sum over objects of the Fuchsian group. You put some kind of weight here that will have several purposes, in particular to get convergence here, because otherwise you're going to some terms of the same size, and then at this point go infinity. You need to put some weight here that to get things to converge. And then once you do this, you're going to get some series that, if it converges nicely, it will have a good transformation rule under it. So it will give rise to some, the coefficients of some form that descends to that descends to the quotient of the disk by the Kleinian group to the Riemann surface. So this is kind of so you want to have this form that changes correctly in the disk to get some form in the surface. And the issue here is that you need to choose k, that's an integer because we're talking about holomorph functions, that is that converge. And what happens is that you can check convergence of this term here, so absolute convergence here, for k equals 2, by observing that what you're doing here, once you integrate over some set, is going to be some transformation just of the change of it's just the Jacobian of the map. And you can, so the average of this Poincaré series, or with absolute value instead of cancellations, is going to be just the sum of the areas of the iterates of your set. So if you select your set conveniently so that it's disjoint of its iterates, then you're going to get something of finite area. And then you get less than infinity, and then you conclude by a distortion argument that the Poincaré series was always convergent. And okay, so that's the argument to get k equals 2 for convergence of the Poincaré series. And so this was kind of originally your interest on k integer and your interest on, well, he was interested in Poincaré, and on constructing these holomorph objects. But you can try to construct other kinds of objects with the Poincaré series. So one thing that you can try to do is construct a measure. And here you are going to put absolute values here and put some exponent that no longer needs to be an integer. And once you do that, you can, for instance, put here, so this direct mass at the point gamma of x, and then you're going to get a measure on the disk that you transform correctly. Well, you have a nice transformation rule according to the, well, there's some kind of mistake there. They will have a nice transformation rule with respect to the action of the group. And what you're interested on, so in general, this measure could be infinite, and or it could be finite. And what's very important is the critical exponent that separates the possibilities of this kind of the total mass of your measure to converge or diverge. And the fact that it's converge or diverge is not dependent on x. Again, the distortion argument. And so the point is that if you look at the critical exponent, you can push the mass. You just had some kind of stupid measure that was just atomic with some atoms that were separated and was inside the unit disk. At the critical exponent, you can push this measure to the boundary of the disk, and you get a measure that is lying on the limit set, which is going to be then so here. So you get this measure lying on the limit set, which you have still good which in principle is a fractal set, and which has a good transformation rule under the under the Fuchsian group. And this will be called the conformal measure due to the existence of this good transformation rule with exponent, the critical exponent. And you could think there is another natural measure that has a good transformation rule that's supported on the limit set, which is just the Hausdorff measure. That's why we're getting to the connection to dimension. So Hausdorff measure of the right dimension would be a very good measure to have the good transformation rule, but it may not exist because the measure could have infinite, at the critical exponent, the Hausdorff measure could be infinite or 0, and in this case, you don't get any measure that to work with. But this measure that I'm talking about will always exist, constructing this way, and will not be exactly exact Hausdorff measure, but will be good enough for it will have good enough geometry. And this kind of ideas developed in the 70s, they generalized to the setting of Klein groups as well. But I'm talking about the simplest possible setting. What you are interested here is the case of a quadratic map, or quadratic-like map. So what you take is, instead of taking the part that everything was nice for the Fuchsian group was inside the disk, the part where everything's very easy for the quadratic-like map is outside the Julia set. So you take a point outside the Julia set, x, here, and then you iterate f backwards from it, and so you look at all points that go at some point to x, and you take the derivative and raise to this exponent minus 10. And if you do this, you're going to produce some kind of, this is the way I wrote, I'm not producing the measure, I'm just producing a number for this. And this thing that you're writing, it will converge for delta equals 2. The same area estimate that I just talked about can be carried on here. So you can produce this Poincaré series, and you can use this also to try to construct conformal measures in the Julia set now, by putting atoms on those ranges. So now there is a more quick, of course, there'll be a connection to dimension using the conformal measures. There is a more quick connection that you can think of that is the following. So what you can do is that there is this fundamental annulus that you can tile. You decompose in two rectangles, let us say. And then you start taking preimages under the dynamics to get tilings in different smaller topological rectangles, which you, as you iterate backwards, you're going to get everything in the complement of the Julia set. And this kind of tiling of the complement of the Julia set has the characteristic of a Whitney tiling, with some way to tile some kind of set with some kind of complicated boundary, where at every point you put a tile that has a size that's comparable to the distance to the bound, to the set that's creating problems, so to the Julia set. So this is a way to kind of explore the geometry of the Julia set from the outside. And indeed, if you know things about this Whitney tiling, you can use this to estimate some kind of dimensions, provided the Lebesgue measure of the set that you're interested in is 0. It could be that your set is kind of big from the inside. Like, if it's too big from the inside, it can be that from the outside you don't see how big it is. And what you get from the estimate doesn't see the whole measure, the whole dimension that it has. It happens. But if the Lebesgue measure is 0, it kind of works fine. So what happens that the critical exponent that you have for the Poincaré series is going to be exactly the critical exponent to get convergence of the diameters of the tiles to some power. And you give a direct estimate on dimension. This was worked out by Bishop originally in the set of Kleinian groups in a direct way. Here's a picture of what I just said. You tile the complement here of some fundamental annulus. Here's tiled in 4 pieces. In yellow and blue, maybe. And then you take a first preimage and you get more tiles here, 8. And another preimage that is 16. And this you approximate in a complicated way the Julia set. But each tile will have this kind of property of being this Whitney property of being far away. Its size is proportional to the distance to the Julia set. So that's a picture here that can be easily produced with a kind of off-shelf computer program. So Poincaré series is a helpful way to try to get the dimension, but the problem is to estimate it. So just a theoretical, in principle, just theoretical tool if you don't know how to kind of estimate if it converges or diverges for which parameters. And here is sometimes it's kind of easier to estimate in situations where you have lots of expansion and the terms kind of decay sufficiently fast. But here is the situation where you have not enough expansion along on your system. That it comes from the critical point, because as you iterate the critical point many times, it comes back as it can be seen or near the critical point. Things that are seen by renormalization means that a large iterate, it is basically like one single iterate of a quadratic map that has some kind of a derivative that's bounded. So very often you get this kind of bounded derivatives as you iterate. And this shows that the terms are kind of difficult to kind of control, and particularly in the direction of showing that the critical exponent is less than 2, to get a little bit more than what the area estimate gives. So that's the problem, that there is a lack of expansion in the critical orbit. What you can do to get something that converges and that can be analyzed is to truncate the Poincaré series. So the Poincaré series sums over all orbits. So you can say, well, let's skip the orbits that go close to the critical orbit. So if it gets to epsilon distance, you don't, or it will be in practice getting to some deep renormalization level, forget about it and just look at all the other orbits. And these will be things that see only the expanding part and are kind of can be analyzed much more simply. All right, so you have this. But at some point, you need a full Poincaré series to get information. And that's where we started doing this in 2001. We used the self-similarity of the basic idea is that due to self-similarity that from the renormalization fixed point, it translates to some structure, to some inner structure of the Poincaré series. So if you have an orbit that's very long and you want to evaluate TFN of Z or of Y. And then, but sometimes there's the iterate, it's away, it's in the expanding part, but sometimes it gets close to the critical point. But then you can iterate using renormalization, and then eventually it does something else. But many iterates appear from the normalization, and so this corresponds to a term that can be corresponds to another orbit of the original map that's kind of further from the critical point. And it's a piece of a Poincare series that's also kind of that also appears. So in the Poincare series, there appear some pieces that after they appear as little pieces of different orbits. So some orbit that appear here will appear as little piece of orbit that appears here, and everything's multiplicative. So there will be some nice combinatoric structure that unfortunately is very difficult to write down. But if you start working out the combinatorics and how you can put terms that and trying to translate into other, renormalize some terms and then accept terms that kind of lie away from the critical orbit and do things like this, you get some kind of nice expressions that is this one. The main expression that is useful for the analysis of fixed points is this one. So you fix a renormalization level n, where you're going to truncate and stop your analysis at this. And after you get in the normalization domain, you're going to try to use the combinatorics to kind of plug the Poincare series into itself. And by doing this, you get some approximate relation that looks like this. It's a quadratic polynomial by accident. There's no reason. It's not because the quadratic-like map. It's just the combinatorics that looks like this. So the Poincare series with exponent delta is kind of can be evaluated approximately as a quadratic polynomial in the Poincare series, on the same Poincare series, with coefficients, coefficients A delta, B delta, and C delta that are truncated Poincare series. So you get those truncated Poincare series, and which means that they can kind of, you can put your hands more easily on those A delta, B delta, and C delta than the P delta directly. And well, the fact that it's just an approximation is, of course, because you have a Poincare series associated to one point, and then you're going to plug in pieces of a Poincare series later, but this is related to another point. After you renormalize, there is a rescaling that takes you to a different point. Everything can be related by a constant, but just by a constant, not by a better than that. So there is kind of and there will be those constants that you need to estimate those constants to see that they are under control. They will depend on the initial geometry, like the shape of the fundamental anodes. There are many things that need to be taken care of. But anyway, once you look at this recursive equation, you don't want to say this for the final Poincare series. You look at, of course, you try to use this to sum the Poincare series. So you have some kind of partial estimate of the Poincare series. You plug in to get a better estimation of the Poincare series. And so you use this as recursive relation to compute P delta. And the question is if it goes to infinity or if it remains finite. So what will be the key issue is the existence of a fixed point for this quadratic polynomial that's kind of stable enough that will survive the fact that you just have an approximate relation. And sometimes it can be done. So what you're going to do is the best way to, for the questions that you are interested in, you are mostly interested whether the critical exponent is equal to 2, so if which will be related to if the Hausdorff dimension is less than 2 or not. And what you can do is evaluate everything for delta equals 2, and then use that the coefficients that are kind of truncated Poincare series, they are nice. They depend continuously on delta near 2. They will be defined and continuous for delta near 2. And then, so the existence of fixed points for the for delta equals 2 will imply fixed points for delta less than 2 as well. And in this perturbative approach, it's nice because the coefficients correspond to areas of certain sets, right? And the exact formula for the coefficients are a little bit complicated, but they involve some manipulations around some expressions with sums and products, some simple expressions involving two quantities that need to be evaluated now. Those are the complicated ones to evaluate, which is, so you have a truncated renormalization level, dip of level n, and you look at the probability is some area scaled by the total area of what your phase dynamical system. What's the probability that you hit the deep renormalization level before you escape? So it's a probability of falling inside and seeing this renormalization level. This gives you something called eta n, depends on the renormalization level. And also, if you start at the renormalization level n, what's the probability that you kind of go outside directly? Actually, at the fundamental annulus here. So you escape directly without kind of coming back, ever coming back to this to the level n. So you go straight to infinity without passing again here. So those are things that can be evaluated in principle, if you know something in several ways. But it's kind of, in practice, a little bit more complicated. So you have, but so to so now you have to plug in many things about the Poincare series and look at recursion between different levels n and n plus 1 and so on, and see what they say. So the existence of fixed point for some level n implies something about level 2n, and there are several things that you put together in this analysis. But basically, it comes down, after you work out these things, that there are some situations where you can decide what's happening. If the eta n, so probability of coming in, is sufficiently large compared to the probability of going out, or if they're opposite, then the critical exponent is less than 2. You compute what happens to this quadratic polynomial, you see a very clear fixed point that stays there. And moreover, if you kind of analyze a little bit more, you see that if eta n is bigger than is much bigger than psi n, this actually is because it's the opposite of what I wrote here. But so if eta n is bigger than psi n, then the Lebesgue measure is positive. So probability of going in is very large compared to the probability of going out. Then this produces positive Lebesgue measure. And in the other possibility, you're going to have house of dimension less than 2. So you see that if this happens, the positive Lebesgue measure case, which is kind of reversed here, so this is eta n much bigger than psi n, then it's a particular case of critical exponent being less than 2. And what this critical exponent is giving here is also some kind of dimension, which is called the hyperbolic dimension. This is the dimension of the expanding part of your dynamical system. So if you look at hyperbolic sets, so those sets where the derivative grows exponentially, so sets that are away from the critical point. So you truncate the Julia set away from the critical point and see what you get. This you get things that are expanding, and you see that you get well, you get some sets, and you can look at the hyperbolic dimension. So that's the soup of all those dimensions. And so it's the dimension of the expanding points in a sense. And this is what's given by the critical exponent. This is what you're seeing from the outside, right? You see those things that can kind of go to a large scale by those expanding dynamics. And if this would happen, then this would be the first example of a rational map for which the house of dimension and the hyperbolic dimension do not coincide. Usually you expect that you have as many expanding points as you have points at all in terms of dimension. But here it should not be the case. You're going to have much more points because the Lebesgue measure is positive, the house of dimension is 2, but the critical exponent is less than 2, the hyperbolic dimension is less than 2. So this would be, at the time that, so this has been coming for a long time, it was unclear. So is it positive or negative? Maybe this cannot exist. All right, so but what we did pretty soon after was to show that the other possibility, okay, so what I need to say a little bit more about this eta n and psi n. Basically, by playing with what they are, you see that the successive eta n, so as you vary the renormalization level, you see that once you pass this, this kind of threshold, so eta n became much bigger than psi n, then they start splitting further and further apart. Psi n starts decreasing exponentially, and eta n stays of the same size. And same thing for the other possibility. So they kind of get in a dichotomy. So at some point, they kind of split, and then it becomes clearer and clearer as you increase n. But the point is that here you can get this from any fixed n allows you to decide, as long as you knew, for instance, this constant. Unfortunately, it's difficult to know exactly. It should depend on this rough geometry of your fundamental annulus, its shape, basically. So, so you have this, and it's just to explain, I need to explain what's the nomenclature, because I'm going to talk random walk without doing any probability so far. What you have to think about, if you look at how does eta n and psi n look like, they look like certain parameters in a random walk. So you have so basically points, they can go outside, eventual escape, or they can go inside and get more and more trapped into renormalization level, deep renormalization levels. So you can think to a certain extent your dynamical system that it's going all around. To a certain moment, it's just you just worry about whether you go outside or you go inside at certain moments. And if you look at this, you could imagine that you, in an approximation, is completely deterministic, but you're doing a random walk. Sometimes you go closer, sometimes you go further away. And what you're measuring here are probabilities of going further away and probabilities of getting closer. And if you look at a random walk like this with some drift, you're going to see exactly this. If there's a drift of going inside, then there will be exponential decay of some probability, and kind of another one remains constant. So if there's drift here, there will be a positive probability of going directly to here, and the exponentially small probability of kind of going up, and things like this. So it behaves pretty much like a random walk, and this can be kind of formalized a little bit more, and kind of getting some kind of contour on this. It's kind of very important later on the kind of more, if you want to generalize beyond fixed points. Anyway, and the point is kind of estimating, getting those drifts. And in our first paper, we found a way to get drift outside by analyzing certain combinatorics that the easiest case to consider are close to Chebyshev map. So Chebyshev map is parameter -2. The Julia set's very thin. It's just an interval. So if you look at certain combinatorics close to Chebyshev, you get you can contour the initial parameters, and you get immediately that eta n is much smaller than psi n. So you get already in one case by directly computing. Okay, so we discovered that sometimes it happens the first case, well, it happens household dimension less than 2, which was kind of already violating this expectation that people had at the time. And what about the Lebesgue measure? Maybe for some other deep reason, this never happens. It's not because Poincaré is just a way to compute things. But there's no, you cannot play with the parameters at all. There are certain fixed points. There are countably many fixed points of renormalization. But maybe there's a good reason that prevents Lebesgue measure to be positive. So that's what, more recently we were able to tackle this question. So this paper is going hopefully to be finished soon. Let me explain how you produce drift towards the critical point in pictures. So this is, again, I showed already this picture, is a renormalization of certain quadratic map. Many things that I wrote kind of resist well under quasi-conformal maps, so it's enough to consider the quadratic map for many things. So you see here, what's this kind of blue part, light blue part, is probably points that go inside this region. And red part are points that escape. So in the constitution of eta n, you're interested in these blue regions. And here inside this ring here, the white region are the points that that escape, and the deep blue are the ones that that come back. So psi n is basically this white region, and eta n is the blue, the light blue region. So this is a certain specific quadratic map. Here's another one. This is going to be a little bit slow because those pictures are very large. So you're going to see that I'm selecting things for which this blue part is getting more important, the white part is diminishing. And the thing that you should have in mind is that the picture looks to be converging as well. Look that the Julia set almost doesn't change anymore. You just have kind of shrinking of those white regions and increasing this blue region. And well, this kind of, it took like 1 month to produce a less picture, that kind of iterating a lot. I will just say that, well, let's see if it can produce it, because I'm clicking here. Oh, okay. And if you look at the parameter set, you're going to get this is the Mandelbrot copies associated, little Mandelbrot copies. They are going to be, you're going to see that they also seem to be converging. Look, they're not changing much more. So what I drew there was, it shows that along a certain sequence of the combinatorics, you seem to be getting where you want. The geometry is remaining under control. You see that the annulus is not changing much. And eventually, it seems that positive drift emerges. So what I did is, if you look at the periods that I consider, it's 7, 18, that's all the periods that I consider. They are basically, this is Fibonacci number Fn plus Fn minus 2, because everything is produced by bifurcating something which is ruled by the golden mean. That's why Fibonacci numbers appear, and then you bifurcate in kind of the most, in the simplest possible way that sums this Fn minus 2 to produce the period. And those are the numbers. They are like closest integers to 1 plus square root of 5 over 2 to the 2k. And, but what you saw is more than that. So that's how I chose those combinatorics, after actually proved the theorem that the pictures were drawn. It shows that there is some limiting behavior. So it suggests a strategy to proving it by observing that there is a limiting behavior that you're getting those pictures, that the geometry remains under control, and just enhance the picture with more and more etas and less psi. And the explanation of this limiting behavior should be explained by an appropriate, since there is some kind of universal or limiting behavior or self-similarity or whatever, there should be a renormalization theory that explains it. And unfortunately, so this renormalization theory, we know what it should be. It should be some Ziegler renormalization theory, because those parameters were chosen by taking a map which has a neutral fixed point. So there is a fixed point with derivative. It's a complex rotation with angle 2 pi times 1 plus square root of 5 over 2. And this kind of maps by Ziegel's theorem has a Ziegel disk. So all points that are nearby, they kind of also rotate and don't escape. So they stay in the Philadelphia set. So you have this kind of lots of points that kind of tend to stay close here, and you avoid initially points escaping. And that's why you expect that this is helpful here. While the Chebyshev map, everything was escaping fast, here at least things stay a long time there. And so this kind of Ziegel disk is what you want to renormalize to try to explain what you saw. And unfortunately, it's difficult to explain rigorously what you saw there. Basically, the point is that you can think that you can construct a fixed point of some renormalization, which should kind of see the Mandelbrot copies that I drew. So the actual little Mandelbrot copies that I showed, they should be trapped in an unstable manifold of a renormalization fixed point acting in a very complicated space somewhere. And how to say theoretically that's big enough to contain some little Mandelbrot set is kind of completely unclear at this point. So the actual rigorous argument that can be done, and for some kind of more complicated combinatorics that exploits what's available, but has some kind of similarities in the end to this, what I drew was kind of simplifying our proof. So we had a proof that works, and then we kind of say what would be, if everything was nice, how it would work out, and I came up with that. So, so what you're going to look for are renormalization fixed points. Instead of going to mean that's 1 plus 1 over 1 plus 1 over 1 blah, 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 you look at things that are closer to the parabolic point. That's 1 plus infinity plus 1 plus infinity and so on, which is 0. So if you have a parabolic point, so it's not no longer a rotation, it's just kind of identity, the derivative. It's some kind of difference, not a Ziegel map. But you can get a renormalization operator for this kind of parabolic limit. And that's what people managed to do. Inushi Shikura developed a renormalization operator, a theory of the renormalization operator of this parabolic limit that survives the bifurcation process and gives the information for this kind of quadratic irrationals of type 1 over n plus 1 over n and so on. So you can kind of control the renormalizations of certain guys. And there is some little control about some piece of the unstable manifold, just along a certain direction that we use to trap the right Mandelbrot copies. So there is complicated. So just to finish about what you get in particular. So there are several consequences of having discovered those kind of Julia sets of Poisson-Lebesgue measure for fixed points of renormalization that they can arise. It's because what we knew before of constructing a Julia set of Poisson-Lebesgue measure was based on unbounded distortion and unbounded geometry. So it's basically what's known in dynamics as Liouvillean mechanism, where it comes from kind of increasing the distortion more and more, and now getting many points that kind of come closer to make points behave in a different way than you would expect them to do. And this also generates some unbounded geometry, and usually connected to non-local connectivity of the Julia sets, so they get very ugly, the Julia sets. While for the fixed point of renormalization, you see that that's not necessarily how it goes. You can produce it with having bounded distortion, like in different scales, you always see the same kind of amount of distortion by renormalizing. Bounded geometry, you can tile everything by pieces that all have kind of same kind of shapes that are under control, and then you're going to have local connectivity. And so this is kind of a clear difference between a Liouvillean mechanism of producing Lebesgue measure and this new Diophantine mechanism that's the first time that has been carried out. And but why is it useful? So I'd like to emphasize the robustness of this. So beyond just renormalization fixed points, what you get from this is that this construction, since you are evaluating some kind of positive drift, and then this kind of random walk argument is kind of stable. If you change a little bit the parameters of what you are doing, it's going to still work fine. So what can be done is to construct many more parameters with a positive house of dimension of parameters. It's going to be an entire horseshoe which have this kind of a Julia set of positively bag measure. And what we are looking at right now, and it's looking kind of, that's going to work, that it's going to resist even deforming things into 2 dimensions. So we're doing everything in 1 complex dimension, but there is a renormalization operator that goes through 2 dimensions. So you renormalize 2-dimensional dynamical systems, which are dissipative, so they contract area. And as you renormalize, they become more and more dissipative until they become infinitely dissipative, so you recover 1-dimensional maps. So this renormalization fixed point, they are also renormalization fixed points for this kind of more complex, this kind of higher dimensional dynamical, renormalization higher dimensional dynamical systems of those anon maps. So by using these properties of the renormalization fixed point, it's imagined that in their stable manifold, you are going to be able to carry out the random walk mechanism. Everything indicates that's true, but we didn't kind of really go through all the details. And this will mean that corresponding to the Julia set of positive bag measure, there will be some strange new kind of, it's very difficult to construct non-trivial attractors for complex anon maps. And it seems that this will lead to construction of some kind of strange new attractor in the complex anon map setting. And also kind of large horseshoes and things like this that are going to possibly be useful in these other settings. So it seems that it's going to be applied much beyond 1-dimensional dynamics. Hopefully, well, at first we have to finish our original preprint, but that's the next question that we're going to be looking at.
Thank you very much, Artur. As we did yesterday and the day before, we are not going to open for questions here because the venue is not really suitable for that. But Artur will be staying throughout the week, so we can just ask him questions during the coffee breaks. Thank you very much.